Okay, Kathy asked about homework problem number 7. In this problem, we have a box that we're pushing across the floor, but we push it 2 different ways. In situation A, we're pushing with a bit of a downward angle, and the box ends up moving at a constant speed when we push it like this. So in the situation A, we're going to figure out what the coefficient of friction is between the box and the floor. Then in situation B, we push with the same amount of force, but now at an upward angle, and we'll figure out what the acceleration is in that situation. Now there's one thing that the problem does that's a little bit tricky or confusing. They don't tell you the mass of the box, they tell you the weight. So they give you the weight of the thing, but remember weight is mg. So if you want the box's mass, it is W divided by G. So just do that, and then from now on, I'll assume we know the mass of the box. So let's answer this first question. What's the coefficient of friction between the box and the floor? Well, I'll analyze this using our standard free body diagrams, Newton's second law procedure. So here's the situation A, and here's the free body diagram. Horizontal, vertical coordinate system. Here's the box. We've got our pushing force, which is down at an angle. There's gravity. And there's a normal force. And there's friction. So ground, box. Ground and box. Earth, box. And the pushing force is U. Pushing on the box. By the way, I drew the pushing force down here. It doesn't matter where on a diagram you draw a vector, as long as the magnitude and direction are correct. But it's more convenient in free body diagrams to have all the vectors start at the origin. So I just took this vector and I slid it so it landed here on the page. Okay, so let's do Newton's second law. Because we're dealing with friction, we do need to look at the y direction so we can get the normal force, so we can figure out the friction force. Sum of the forces in y equals m(a) y. This box is not accelerating in the y direction. It's not moving up or down, so the right-hand side of that equation is 0. We've got normal force, and we've got gravity, and we have the y component of that push. And if you look at this right triangle, that y component is opposite to angle theta. So it'll be F sine theta. And from that, we can conclude that the normal force, I'll drop all these subscripts, equals gravity force minus plus F sine theta, or mg plus F sine theta. Now something to keep in mind already, if you just have an object sitting on the surface, sitting on the ground, the normal force on the object equals its weight, mg. In this situation, the normal force is bigger than the weight of the box. That's because we're pushing the thing down. So in order to keep the box from falling through the floor has to push up with more normal force than usual. So this normal force has this additional amount that comes from the fact that we're pushing down on the box a little bit. Let's look at Newton's second law on X. The problem tells us that the box is moving at a constant speed. So that means the x acceleration in part A is 0. So what do we have in x? We've got the x component of this push, that gets a cosine. Minus the friction force. So F cos theta equals friction force mu times N, and we just figured out that N was mg plus F sine theta. So finally, we get an expression for the coefficient of friction. It is F cos theta over mg plus F sine theta. And that's your answer to part A. While I'm thinking about it, I need to mention something that I have noticed, a little mistake I noticed a few people doing. This thing mu is called the coefficient of friction. It is not a force. That is not the friction force. The friction force, F, is mu times N. Mu times the normal force. Mu by itself is not a force. In fact, it's just a number. It doesn't even have any units. Coefficient of friction, friction force. Okay, what is the acceleration of the box in part B? Let me erase this. Draw a new free body diagram. Okay, so we got that. Part B, free body diagram is similar. There's just one difference now. The difference is that we are applying this force in a slightly upward direction. Yeah, I'm going to erase all this stuff because you can rewind the video if you need to see it again. Okay, so again, we need to do the y direction first because friction is involved. There's no acceleration in y, the box is not moving up or down. So we've got normal force plus your push again, it has a sign because the y component is opposite to that angle theta. And we've got gravity equals 0. So the normal force this time, and again, I'll get rid of these subscripts so it's easier to write. No subscripts. It's W minus F sine theta over mg minus F sine theta. This time, the normal force is less than it would be if the box were just sitting there untouched, because by applying this force upward, you're lifting it a little bit. So the ground doesn't have to support it as much. Remember, N is what the ground is doing to the box. So it supports less than the box's full weight because you are helping to pick it up ever so slightly. By the way, that's going to reduce the amount of friction that the box experiences, which is why in part B, it's going to have some non-zero acceleration. Okay, X direction, we're not going to assume acceleration is 0 anymore. We'll just figure out what it's going to be. So we have two forces. We have the X component of your push, and we have friction. So that is F cosine theta minus mu times N. Friction force is mu times N. Here's our N for this situation, mg minus F sine theta. And the last thing to do is to divide both sides by A, and we'll get that acceleration. So the most interesting thing about this problem, I think, is the effect that this push has on the friction force in the problem. By pushing the box slightly downward, you increase the normal force between the box and the ground, which increases the friction force. By pulling the box slightly upward, you reduce the force between the box and the ground, which reduces the friction force.